In this video, I want to talk about matching graphs with polynomial functions. So I'm actually going to go over to Alex and we're going to look at some polynomial functions, but first I want to talk about the things we're going to look for. So the things we're going to look for are the degree of the polynomial and how many turning points the graph has. So the degree of the polynomial is the highest exponent. And polynomials with whatever degree can have one less than that turning points. So the degree is often called n. So that would mean that the first term would be like x to the n, right? And whatever that is, x to the fourth or x to the third or x squared. And then each polynomial function has at most one less turning point than the degree. So the turning points can be at most n minus 1. So for example, x to the third function might look something like this. And so it has one turning point here and one turning point here. So it has two turning points because it's an x to the third. You can also think about x squared as a parabola. It has one turning point, right? So it's x squared has one turning point. A turning point is just a place where the graph turns and starts going another way. An x to the fourth graph often looks kind of like a W, and it has three turning points, 1, 2, 3. So it can have less than this, but it can't have any more. So at most, n minus 1 turning points. So we want to look at the degree. We also want to look for the x-intercepts and also possibly for y-intercepts. Y-intercepts may be harder to find in the equation, but we can always look for the y-intercept. So the y-intercept is always that last term, the just number part, the term that involves only a number. But we might also look for x-intercepts and see what happens there. We also want to look at the leading coefficient. So the leading coefficient is the number that's in front of the x to the n. So it's like k x to the n. Whatever that first term is, whatever the number here is, we want to look at if it's positive or negative especially. So if it's positive, then it's going to be up opening, or if it's a parabola, it would look like this, or if it's a x to the fourth, it would look like this. If it's x to the third, it would look like this. So this is if it's positive. If it's negative, it would be down opening, or the W would look like an M, or the x to the third would look backwards, would start high and go low instead of starting low and going high. So we're going to look for those things and see if we can use that to match our graphs with a polynomial function. One more thing that we might look for is, let's just put a number 4 over here, is any places where we have a repeated root. So a repeated root regular roots are where the graph crosses through the x-axis, right? But in a repeated root, so this is a regular root, a single root, let's say. But in a repeated root, the graph, instead of crossing through, it's going to hit and bounce. So instead of crossing the x-axis, it's going to bounce and go back the other way. So this is a repeated root. So that's another feature of a polynomial that we might be able to use to distinguish which one's which. Okay, so now let's go to Alex. So you can see that we're matching graphs with polynomial functions. And I'm going to look here and let's first look at g of x. So g of x is kind of factored. If we multiply that out, it would be x to the third. So we're looking for an x to the third, and it's going to be a positive first term. That leading coefficient is going to be positive, which means it's going to start low and go high like this guy. So it's going to start low and go high, and it's going to be an x to the third. Now all of these look like x to the third types of graphs. So starting low and going high could be any of these first four. It starts low and goes high, starts low and goes high, starts low, goes high, starts low, goes high. These ones are backwards. They start with something negative, but any of these first four could be G. So now I want to look at my x and y intercepts. So if I were to multiply all of this out, my y-intercept would be 9, right? Because if I were to, that very last term, if I were to multiply it out, it would be plus 9. So that's a hint that it looks like it might be this one, because this one's positive on the y-axis. This one has 0 for a y-intercept. This one has something negative, and this one, it could be. I don't know. We don't know what the scale is on that. So let's keep looking. We also know that the graph crosses the x-axis at 1. X equals 1 is a root. So let's look for any of these where x equals 1 is a root. So this has x equals 1 as a root. This one doesn't, and this one doesn't. This one also has x equals 1 as a root, but we've already eliminated this one. So I think it's going to be B. So let's think about the other things that we could do to check, though. So if we were to factor this into x plus 3x minus 3, we would have roots at plus and minus 3. So we have roots at negative 3 and positive 3. So that looks pretty good. And so this is definitely, it looks like it's definitely graph B. So we're going to go with graph B. Now we're going to look at h of x. So we already determined that a positive leading coefficient, all of these four had a positive leading coefficient. So it has to be one of these two. Now, one thing I'm noticing right away is that there's no term all by itself here. There's no just number. And that means that when x equals 0, y equals 0. So it goes through the origin. Well, of these two graphs, this one is the only one that goes through the origin. So we can bet that this is definitely graph C. So this one is graph C. And we can check our answer. And we're correct. Let's try one more. So in this case, this is f of x is x plus 4 squared, which means that when we multiply that out, that would be x squared times another x squared. So this is going to be an x to the 4th polynomial. So an x to the 4th polynomial looks like a w or an m. So we're looking at this, this, or this. So now we need to figure out, is it going to look like a w or an m? So w is the upward facing one. So if I multiply x squared times x squared, that's going to be positive. So it needs to be an upward facing one. Okay, so it's definitely D or F. Now, I noticed that negative 4 is a repeated root. That means that it touches the x-axis and goes back the other way. Now, they both actually have that. So negative 4 is a repeated root. It bounces off the x-axis, but they both have that. So that doesn't actually help me. If I factor this out, we can look at, so here we can look at y-intercepts, or we can look at factoring this out. Let's look at both. So here, if we factor this out, it's going to be x plus 1, x minus 1, which means that both positive and negative 1 are going to be roots. So negative 1 and positive 1 are here. This one only has 1, and it's a repeated root again, and that's not what we have here. So I think it's going to be D. We could also check the y-intercept. So the y-intercept is going to be 4 squared is 16 times negative 1. It's going to be negative 16. The y-intercept here is positive. So this is definitely going to be graph D. Now this one looks pretty familiar. It might be one of the ones we had before. Negative 2x to the third plus 8x squared. So in this case, this is a negative x to the third polynomial, which means this would be a positive x to the third polynomial. So this is negative, and this one's negative. Now, we know that this one goes through 0, 0, because it has no plus a plain number or minus a plain number, but actually both of these go through 0, 0. So that's not helping us entirely. So now we need to probably look at repeated roots here. So this one has a repeated root at 0, whereas this one has a repeated root at 4. So if we were to factor this out, it would be x squared times something, right? And so we're going to have a repeated root at 0. So a repeated root at 0 looks like this. It's going to bounce at 0. So I would go with graph C in this case. So that was actually a little tougher than the last one, even though I think it was the same problem. Okay, so let's go ahead and check. And we got them right. Very good. Okay, so that's how you match graphs with polynomial functions.